It says here, draw the correct product for the following diels alder reaction. So I have here, this is a cyclopentadiene, right? Oh gosh. Pentadiene plus another cyclopentadiene. What is that going to give me? Sorry. Pentadiene. Oh no, that's a hexagon now. It's very hard to draw pentagons on my tablet. Okay, there we go. So I have two cyclopentadienes. Again, this is a 5. I'm going to draw. This is a 5 carbon ring. 5. Sorry, I'll just write 5. It's a 5C ring. This is a 5C ring. And what it says here, it says draw the correct product for the diels alder. So I know it's a diels alder reaction, right? So if you recall, what is a diels alder reaction here? A diels alder, right? So remember, in a diels alder reaction, we have something called, we need a diene and a dienophile, right? Dienophile. So if you recall, one of us, the simplest diels alder, you need it requires a cis formation of an alkene. So something like this. Like it's cis right now. It's cis right now. It's the methyl group, or the side groups are on the same side. And then if I add this with just the ethylene, what I'm going to get is a cyclohexene with a double bond, right? So again, this is another form of an alkylation, but it's like, you can think of it as like we have double bonds and they're electron rich, and they're reorganizing themselves to form new carbon-carbon bonds. So for this mechanism here, what I can do is I can draw, this is electron rich, right? So what it does is it's going to go into this ring here. This ring is going to move this way, and this ring is going to move up. So I'm breaking two pi bonds. I'm breaking two bi bonds, which are these two bonds. I'm breaking, and I'm creating one pi bond, right? Which is the product here. I'm creating a pi bond, right? So again, I have three. So I had 3 pi bonds before. So I'm gonna break 2. I'm left with break 2, or I can, in this case, it actually breaks all 3, right? I'm breaking this double bond, and this double bond. So I can think of it as breaking 3 pi bonds, or breaking all my bonds, breaking all my double bonds. And then I'm going to create new pi bond, right? Or it's going to create a new pi bond, which is this guy here. So how would that relate to this ring here? So again, take a moment to think about this. Where is my diene? Where's my dienophile? Because in this case, it's actually the exact same, right? It's the exact same structure here. So which one's my diene and which one's my dienophile, right? Where are my electrons? Where are the double bonds going to move? Where are my electrons going? So think about this for a minute. This is actually it's a very, very difficult problem. So think about this for a quick moment, and then we will talk about what product it's going to make. Because again, if you count the carbons here, we have 1, 2, 3, and 4, right? Let me count the carbons for you. We have 1, 2, 3, and 4. This is 5 and 6, right? Which means my product here has to have 6 carbons. So if I have 5, because we're not losing carbons, you can't lose carbons randomly, right? So we have 5 carbons here, 5 carbons here, which means my product has to have 10 carbons, right? It's a 10 carbon, right? So again, what would I create if I were to combine both rings together? So I'm going to give you a hint. 2 cyclic structures, right? I have 2. So this is one cyclic structure, and this is another cyclic structure, which means my product, when I combine them both, I make a bicyclic structure, bicyclic structure, right? When we talk about bicyclic structures, they look something like this, right? They look something like this. Hopefully if I draw this correctly, it's not that bad. Actually, hold up. Let me redraw this. Yeah, they look something like that, right? You have something that's sticking up from the plane, right? 1, 2, 3. Again, this is not accurate of the carbons, but this is example of a bicyclic structure, right? Or you can draw something like, instead of a stick here, you could draw like a little V here to say it's bicyclic. It doesn't really matter. I like to draw the stick here because it's pointing up, right? So again, this here isn't 10 carbons here, right? I have a bicyclic structure, but it's not 10 carbons here. So I have 1, 2, 3, 4, 5, 6, 7. So I'm seeing 3 more carbons, which means I have to have something here, right? So I have, this is 7, which is I have 8. Oh, I didn't move. I didn't want to move this. Sorry. I have 8. This is 8, 9, and I guess 10 would go this way, right? So I have 1, 2, 3, 4, 5, 6, 7, 8. Oh no, this is 9. That's wrong. Sorry. So I would have to go. I'm 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So that's going to be my cyclic structure. Right? Let me count again just to make sure if I have the right amount of carbons. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 carbons in total. So this here are the bicyclic structures, right? And again, where are my double bonds, right? Where it's going to go? Where is it going to go? So I told you that it's going to break all my double bonds. It's going to create one new pi bond, right? So if I have, and this here I have three pi bonds, right? To break 3 pi bonds, it's going to create a new pi bond. So which means in this case, I'm going to break 3 of them and create a new one. So in this case, my mechanism, I could draw it out as, it doesn't matter which one's the diene and the dinephile because they're both the same structure. So I'm going to take this double bond, for example. It's going to attack this double bond here. This is going to shift up. This is going to get out. So which means I'm breaking these two. I'm breaking this double bond here and these double bonds, and I'm going to create one. So the net gain in this case is I'm going to net, I'm going to lose 2 pi bonds, which means I'm going to lose 2 pi bonds. I'm going to make a new bond here on this side of the structure, right? Which means I could write my double bonds and be like this, right? I'm going to create one new one, right? Remember, if I break 3 and I create one new, the net loss is that I lose 2 pi bonds, right? So that's why I only have 1, 2, and 3, and I'm making one new one, right? And then for this, with this guy here, this guy's not touched, right? So it's not participating in the diels alder, which means this here is on the other side of the cyclic structure. So I can write this. This one would be on this side here, right? So this here is my diels alder reaction for a. This would be a 2. This is a diels alder reaction alkylation. This is a diels alder reaction of 2 cyclopentadienes, and that's going to be my answer for this problem here. I'm just going to check if that's correct. And again, they made some sort of I like how they drew the mechanism here. Again, this goes away, this comes in, this comes out, so that's fine. And they get 1 here. They have the point here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 here, and then I have the double bond here. So they drew it like a house kind of thing. It doesn't matter how you draw it, but I drew it correctly as well. So it doesn't matter as long as it's on the same 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. I believe it's there. Is it 1, 2, 3? 1, 2, 3, 4. Yeah, 1, 2, 3. 1, 2, 3, 4. Give me a second. Let me just count. 1, 2, 3, 4 has a double. 1, 2, 3. 1, 2, 3, 4 has a double one. Yeah. So this is the same structure as what they have here. They add a heat and it's 1 to 4 cycles, right? So again, diels alder simply just needs heat, right? So I usually write like a triangle or something like that to prove that this is a diels alder reaction, or I simply say DA or something like that. It doesn't really matter. But again, this syn addition is stereospecific, like all diels alder reactions, right? So I like this solution. This is a perfect solution and great step by step showing the mechanism of a diels alder reaction. So this here is correct. Nice. So the tricky thing here is the bicyclic structures. We have 2 cyclic structures. It's going to create a new bicyclic structure. So this is actually a very difficult concept because it's something that again, it's very like this is organic too now at this point. So I'm going to limit.